section 2.5 is about transformations, but before we can do the transformations, we have to know what these original functions look like. So I call them the parent functions, meaning this is what they look like if we have not shifted them up, down, left, right, stretched them or anything, okay? This is just the typical what they would look like. Because on this test, I'm going to be having us do some of this graphing, and you guys are not going to be able to use your graphing calculator. So the whole, the whole idea is that you're supposed to be able to do these graphs by hand, not just plug it into your calculator and graph off, draw what you see on the calculator. So not the whole test will it be gone, just on some graphing parts. You'll get it for the other parts, okay? So the first one is a constant function. What's it mean to be constant? It just means it's the same, right? So notice on the function, it's just, and the key word, guys, these are functions. So all of them are going to pass that vertical line test where each x has one y and so forth. So they're not going to say y equals. They're going to have f of x equals because it's letting us know it's a function. All right. B, guys, is just that y-intercept, right? It's just a number. So this is just the number. It's the y-intercept, whatever that may be. Okay? They like to keep it generic, though, so that's why they use B. So how we're going to graph these is every graph is going to have, I think every graph, I might be lying. No, every graph other than one will have 5 points, the other one will have 4 points. So how do we graph this? Good old-fashioned T-chart. X's that we're going to pick on this, let's just pick -2, -1, 0, 1, 2. So most of these functions, guys, we're going to pick a couple to the left of the origin, and then a couple to the right of the origin and just see what happens. Well, remember what function notation means. It means plug in your x value and see what happens to your y. But what do we notice about this y? It's always going to be what? It's going to just be that constant b, right? There's no x to plug in. So really, all these are just going to have a y value of b. And I know that's really generic, but it just means it's a horizontal line, guys, okay? So let's just make b like this random mark right here. It doesn't matter. Don't even count a certain amount. Don't worry about where you put it. Just put a random mark up there. Call it b. And so we'll count over 2, and we'll go up to b. We'll count over 1. We'll go up to b. At 0, we're at b. At 1, we're at b. At 2, we're at b, right? So we're just drawing that horizontal line through b. And again, you don't have to match where I put my b exactly because we don't know what b is. It could be positive, it could be negative. We don't know. It's just the y thing, okay? So this is the most plain generic graph we could have. It's just a horizontal line through whatever that y-intercept is. The next function, guys, is called the identity function. And what's it mean for identity? It means yourself, right? So what's special about the identity function is that just whatever x you plug in, that's also the y value, right? So notice if you plug in x, it is your f of x, all right? So we're going to do a T-chart for him. I'm going to pick the exact same x values that I did over there. So -2, -1, 0, 1, 2. And then how do we come up with the y values? Well, remember, the whole idea is you plug the x in, and that's going to be your function. Well, if you plug -2 in for x, what do you get? -2, right? If you plug -1 in for x, what do you get? -1. If you plug in 0, you get 0. If you plug in 1, you get 1. And if you plug in 2, it's called the identity function for a reason. Whatever you plug in for x, that's what pops out for y, okay? So what you'll notice when you graph these points is that they're your just perfect line. It goes through the origin. The slope is just up 1 over 1. You'll see that as you plot your points, okay? So we'll plot -2, -2. We'll plot -1, -1. We'll plot the origin 0, 0. We'll plot 1, 1. We'll plot 2, 2. Okay? And just notice it's going to kind of diagonally cut across all those squares. And you've already kind of seen a version of this being transformed. You're used to the equation y equals mx plus b, right? So that m in front of your x, it makes it a steep line or a shallow line. That will be a transformation we'll talk about. And then that plus b we'll talk about, but that was your y-intercept, right? It's where that line crossed the y-axis, I apologize. So you've already kind of done transformations with lines without realizing it. All right, so the next one, guys, down here, is just your square, or it's also known as your quadratic So we've seen quadratics in the sense that we've factored them, but they've been way more complicated than just x squared. They've been x squared plus 3x plus 2 or something like that, right? So this is your typical parabola. Again, my t-chart I'm picking for my x's are just going to be those couple negative ones, -2, -1, 0, 1, and 2. But what's going to happen when we plug in each of those x values to the function? We have to do what to each of those functions? Square them, right? What happens when you square a negative? It's positive, okay? So this is going to be a perfect example of an even function that we talked about yesterday, where opposite x values have the same y values, right? What do you get when you square -2? You get 4. What do you get when you square -1? You get 1, 0, 0, right? And then 1, 4 again. All right? So let's just go over 2 to the left and go up 4, 1, 2, 3, 4, plot that point. Go over 1 to the left, go up 1, plot that point. 0, 0, and then over 1, up 1, and then over 2, up 4. Okay? As best as you can, don't make it a V. Try to make it curvy, okay? So we're going to curve up through these points, and we're going to curve up through these points. All right? So again, that's just your quadratic where we have not moved it left, right, up, down any. We've just taken each of our x values and we squared them. We could go out further to 3, -3. What would our y values be? +9. Okay? The next one, number 4, guys, is the cube, or I call it cubic function. It's very similar to the quadratic where we just plug in x and then we just raise it to a certain power. But keep in mind when you raise negatives to odd powers that your values stay negative. So we'll still use the same x values of -2, -1, 0, 1, 2. But now we're going to cube them. So, like I said, the negatives will stay negative when you cube it. The positives will stay positive. So 2 cubes is 8. So -2 cubed is -8. And then -1 is -1, 0. And then we'll just have +1, +8. Okay? So this is the one I call like the snake function once you graph it. So we have -2, but we're going to go all the way down to -8. Then we have -1, 1. And then we have 0, 0 at the origin. And then we have 1, 1, and then +2 go up to 8. And again, try to make it as curvy as possible. So they're kind of like half parabolas. So we'll make it go up and be curvy, and then we'll try to curve it down like that. And we saw this briefly yesterday when we were talking about origin symmetry, right? So this would be considered an odd function. Notice its power is odd. And that if we folded it twice, once across the y and then once across the x or vice versa, it would fold on itself, so it has origin symmetry. Okay? So I usually refer to this as the parabola, the parabolic, okay? And then I refer to this one as the snake, the guy that kind of makes his way through the origin. Okay? All right, so the second page are things that are not as common. So like, up until now, you might have seen these in an algebra class before, whether that be here or at high school. These next ones are just maybe not as common because we have to do some kind of weird things, all right? So this one's called the square root function, and what's interesting about the square root function is if we had y squared, we have a parabola on its side, but it wouldn't be considered a function. So what they did was they just took the positive root, so we're only taking like one arm of the quadratic, all right? So how do I come up with the x values for this? This is the one where I only have 4 x values, because can we take a square root of a negative number? No, right? So remember when we're talking about domain, what's the domain of square root? It must be 0 or higher. So my x values for this one, guys, are 0 and higher, but then I pick perfect squares, so it's easy to take the square root and get a nice even f of x value, right? So 0 is the first one I pick because the square root of 0 is really easy to find. The next x value I pick is 1, and then what's the next perfect square? 4, and then 9. We're not going to go past that because our graph only goes over 10 units, all right? So how do we get the y values for each of these x values? You just plug them in and find the square roots of each of them. So what's the square root of 0? 0. What's the square root of 1? 1. And then what do we get for the next two? 2 and 3, okay? Because we're square rooting, not squaring, right? Okay? So it is kind of like the opposite of that quadratic. All right, so when you graph this, it ends up being half a parabola pushed over on its side, okay? So we'll be at 0, 0, but then we'll go over 1, up 1. And then now, since we're square rooting, we're going to go to that perfect square of 4, 1, 2, 3, 4, and then go up 2. And again, since we're square rooting, we're going to that perfect square of 9, and we're going to go up 3. So notice, again, it's like that parabola pushed over on its side. So try to curve it as much as you can. If we had the other half, how would you graph the other half? So like some of us are like, how do you graph this? If you wanted to graph the other half, in your y equals button on your calculator, you could graph the square root of x, but you could also graph the negative square root of x, and it would graph the second part of this function. But since it's a function, we can't do that second part. So that's it, okay? Notice you can see that restriction of a domain. We're only going from 0 and on because you can't take square roots of negatives. What about odd roots, though? Can you take odd roots of negative numbers? You sure can. So what I'm going to do is I'm going to do something similar to what I did on the left. I'm going to use perfect cubes. So then when I take the cube root, it's a nice, pretty number. So over here, my x I'm going to start with is negative 8. What's my next perfect cube? Negative 1. And then 0, 1, positive 8. And again, my reasoning is I want a little to the left, I want a little to the right, and I want the origin if possible. And you guys, you could have picked negative 1, negative 2, negative 3, but what's the cube root of negative 2? Something really ugly. Like you know, so pick numbers that are pretty and will come out nice. All right, so what's the cube root of negative 8? If we're working backwards, we're going to have negative 2. What's the cube root of negative 1? Negative 1. What's the cube root of 0? 0. What's the cube root of 1? 1. And what's the cube root of positive 8? Positive 2. When you go to graph this, notice it looks like our cubic function, but just pushed over. He's going the other direction, okay? So we're going to go all the way out to negative 8. We're going to go down 2. Then we're going to go out 1 and down 1. Then we're going to go to 0, 0. Then we're going to graph 1, 1. And then 8, 2. Okay? And again, try to draw them as like half parabolas, kind of like so they're curvy. And then when you get to the origin, curve the other way. So again, this is just kind of, it's called the inverse of the cubic function, which we'll talk about that later in the year. But it's just that snake pushed over on its side. All right? All right, these last two are kind of weird. Absolute value we saw yesterday. I used it as an example for that y-axis symmetry, okay? So I'm going to go back to my typical x values, negative 2, negative 1, 0, 2, okay? And then what do we know about absolute value when you place numbers into absolute value? What always happens? They become positive. And even if they were positive, they stay positive, right? So they stay themselves, but they become positive if they were negative, all right? So the absolute value of negative 2 is a positive 2. We have a positive 1, a 0, a 1, a 2. So what this basically ends up being, it's like that identity function we graphed on the front, but they cut like the lower left-hand quadrant and flipped it over, okay? So we're going to end up making a perfect V. So negative 2, positive 2, negative 1, positive 1, 0, 1, 1, 2, 2. And again, if you wanted to, you could go further out, but notice it's just going to be that perfect V shape. I'm not a very good grapher. If you miss your line, or your dots, you just make your line a little thicker to try to go through them, okay? All right, the reciprocal function is probably the most awkward to graph because think about domain. What x value can we not use on this one? 0. So that's kind of weird. So we're not going to be graphing on the y-axis at all. But to really get a full effect of what the reciprocal function looks like, we're going to graph some fractions as well, okay? So this kind of has a more awkward t-chart. So we'll start at negative 2. We'll go to negative 1. But since we can't go to 0, we'll just go a little bit closer to 0. So we'll go to negative 1/2. And we can't do 0, right? So then we'll go to positive 1/2, positive 1, positive 2. So again, we can't do 0, so that's kind of what my line is. It's a line through the middle. We can't do him, but we want to see what happens to our graph when we get close to 0, since we can't graph it. All right, so what does the reciprocal function mean? It means just the flip of it, right? So -2, if you go plug him in for x, what do we get? We get -1/2, right? When you plug him in, where is he hanging out? At the bottom. AKA, what's the reciprocal of -2? -1/2, right? Because reciprocal means flip it over. So 2 right now is over 1, but the reciprocal of it would be 1/2, right? So it'd be -1/2. What's the reciprocal of -1? It's just going to be -1, right? And then this is what's interesting. What is the reciprocal of -1/2? When we flip it, it'll become what? -2. Perfect. So what you're going to notice, guys, even though we can't graph 0, the closer we get to 0, the deeper or higher our y values are going to go. All right, so positive 1/2, its reciprocal will just be positive 2. Positive 1 will be 1, and then positive 2 will be 1/2, because we want the reciprocal of it, right? Because we're just plugging it in for x, so it's just going in the bottom. If we wanted to go further out, we could. We could use 5 or 10, but you'll see the further out you go, the closer you are to the x-axis, because 1/10 is very small, right? 1/5 is a little bit bigger, and so forth. So let's go to -2, and as best as you can, try to graph halfway down. And then we'll go to -1, -1, and we'll just plot him right there. And then we're going to go to -1/2. So again, try to plot it as perfectly as you can, -1/2, but then we're going to go down to -2. And we'll talk about what's happening there, okay? Let's go plot our other ones. At 1/2, positive 1/2, we go up to 2. At positive 1, we're at 1. And at positive 2, we're at 1/2. Okay? And what it is, guys, it's a curve within your first and third quadrants that really hug the axes, okay? What do I mean by that? That means if this was 1/2, if we could get more exact, like 1/4, what's the reciprocal of 1/4? 4, so he'd be even higher up. Or if we could potentially graph a 10th, what's the reciprocal of a 10th? 10. So what you're going to notice, guys, is this is just a curve that goes closer and closer to your y-axis and closer to your x-axis. But you never cross it. Have you guys heard of the terms asymptote? Or asymptotically, okay? Okay, so an asymptote is just a, like, invisible line. Like, it's not part of your graph, but it's a line that your graph approaches and approaches and approaches and gets closer to, but may not cross it, okay? So here you'll see that the x and the y-axis are asymptotes, where our graph are getting closer and closer and closer to them, but we're not going to actually and then we're going to just try to do the equivalent, guys, down in quadrant 3. As best as you can, hug that x-axis, go through your 3 points, and then hug the y-axis. And there you have the reciprocal function. Okay, he's the most awkward. We'll talk a little bit more about rational functions, meaning where we have like a denominator and stuff, but that's in a whole different chapter. Okay, so what we want to do next is get our graphing calculators out, if you haven't. We are going to discover the rules of transforming. What does that mean? When you see something added on to the back of a function, so notice what I'm going to write down here, we're going to find out what does that mean our function is doing. All right, so I know I don't have anything written there, but let's write x squared for our a, okay? So on the bottom, we're going to first do vertical and horizontal translations. That's what our next move is, guys. So now that we have our parent functions, 1 through 8, we are going to start moving them, stretching them, shrinking them, all kinds of stuff. So this is going to be very intense because we have to realize all these different numbers, depending on what location they are going to do something different to our graph, okay? So first here, let's graph the following on our calculator. This one we don't really need a graph on our calculator because we already know what it's going to look like. Your x squared function, remember, just means pick a couple x's to the left of the origin, to the right of the origin, and square them, right? So -2 went up to 4. I know it's really tiny. 1, 2, 3, 4. -1 went up to 1. 0, 0, 1, 1, 2, 4, okay? So remember, our original quadratic, our little square function, just looks like a parabola, okay? But in our graphing calculator, what we're going to do, we're going to put that in our y1 spot. So we have him kind of as our baseline data, right? Nothing's happening to him. He's like our placebo, right? He's going to hang out as we do other things to him. So how do we graph on our calculator, guys? Up here in your left-hand corner of your screen, we have a y equals. Clear out anything that might potentially be there, okay? And then your variable is just right here by the alpha button, so we'll hit x. And then the square is just right down here below x -1. Or you can write ℏ2, it doesn't matter, okay? I'm going to hit graph, and then mine's not going to show up because I'm like zoomed in from when we did statistics and stuff. So after it's kind of stopped moving, I'm going to hit zoom, and then see how it says standard on number 6? It gets you back to that normal like 10:10 viewing window, okay? So Corey, I just hit the y equals button, and I typed my x squared in there, and I hit graph. And when I didn't see it come up, I hit zoom and then 6 to get my standard viewing window. So that's our normal parabola, okay? Let's leave him there in our y equals, y1, excuse me. And in y2, let's type this, x squared plus 2, okay? X squared plus 2. So what we're going to do is we're going to go back to our function. We're going to go to y equals. In your y1, leave our normal one. And then in y2, let's go ahead and type x squared and then plus 2. So your guy that was already there stayed there. But then what did you notice happened to our graph when we put a plus 2 there? It went up 2, exactly. And that's exactly what I do. Is like I think, okay, where was the original like vertex? It was at 0, 0. So now where's it been pushed up to? 0, 2. So all of our points we just plotted on the original graph, they just went up 2 units, right? So instead of 0, 0, we're at 0, 2. Instead of at 1, 1, we're at 1, 3. Instead of at -1, 1, we're at -1, 3. And that's enough to kind of get the shape going, guys. You don't have to be that exact. We just want to kind of see the pattern that's happening. So now that you saw that, you probably can guess what our next thing is going to do. I'm going to type x squared minus 3 in our y3, okay? And you can probably guess what that's going to do, guys. If a plusing made it go up, what's a minusing going to do? Make it go down. And that's exactly what happens. This is where I get really excited if somebody has a colored graphing calculator. I know it's like you're a math teacher, win, ... But the graphing calculators actually graph each individual graph in a different color. So like the baseline graph would be a black, but then that one that we moved up might be a blue, and the other one might be a red. So it's kind of cool that you can see them and see what's going on. So again, we don't have to be super picky when we go to graph it. Just make sure that vertex that you have at 0, 0 has been bumped down to 0, 3. 1, 2, 3, right? And then usually we're just over 1, up 1 from there, and you get the general idea of what the graph looks like. We don't have to be super picky. We just want to discover the rule. And that's basically what we're doing right now. So as much as I can, I try to have you like discover or come up with rules before I just kind of tell you what they are. So what is the rule, guys? When we add something to the back of our function, what's it do to our graph? It bumps it up, right? And then if we subtract something on the back of our graph, it just moves it down. All right, so then we're going to talk about horizontal shifts, and then we'll have enough to like fill in our boxes, which are the rules. So x squareds are our tip. Do I do x squared or do I something? I think I do something different just to, so no I don't. I'm boring. Okay, so x squared is going to be our baseline graph again. So go ahead and graph 0, 0, 1, 1, -1, 1, and get that general shape going. Okay? But this time I'm going to do something to our function where it's going to not move it vertically, it's going to move it horizontally. And see if you can notice the difference in how it's written compared to when we moved it vertically. Okay? So we are going to do, what did I do? I did the quantity x plus 3 squared, like that. So in our graph, what I'm going to do is I'm going to go to my y equals. I'm going to still leave my baseline guy there, but I'm going to clear out my other two. And in y2, I'm going to put parentheses x plus 3, the quantity squared, and see what happens. So my original guy should be there. And then what happens when I add plus 3 to it, it actually shifts it to the left. To me, and I don't know if like I can always convince my class, but to me, that seems like the opposite of what it should do. Is anybody with me that when you add plus 3 in there, you think it should be shifting it to the right? okay? So that's how I remember all the horizontal stuff. All the horizontal stuff ends up being the opposite of what you like intuitively want to do, okay? And that's how I remember. I'm like, oh, I want to move it to the right, so that means I must move it to the left, all right? So again, don't be super picky, but just move your origin point 0, 0, 3 spots to the left. 1, 2, 3. And again, just go up 1, over 1 from there to get your general shape of the graph. Sorry, my graphs are really scary looking. Okay, and then the last one, I'm going to do quantity x minus 2 squared. And so then you guys can guess probably without even putting it in your calculator, what's that going to do to our original function? Shift it to the right. And again, it's the opposite of what I would think. I think minus 2, okay, I need to be moving to the left. Minus 2, you're actually moving to the right. And so I can just prove it real quick. So we'll just do x minus 2, quantity squared, and you'll see that we already have these two, and what happens over here, one's drawn to the right. When it comes to these translations, I don't really expect for you to move every single point, but move a couple so we know the general idea of it. Usually 3 is enough. Oh.
We got 4 more minutes.
Thank you. Okay, so what I'll do is I will fill in these boxes and then I'll stop the recording, and that'll be a good place to take it up. Okay, so you already helped me with these 2 parts. When we do vertical shifts, notice how they're presenting it, guys. They're saying f of x. That's just your parent function, okay? So what function are we starting with? Are we starting with x squared or the square root of x, okay? So this is always the parent function, and we're strictly just adding or subtracting something on the back. Well, that's what we just did on the bottom here, right? Here's our parent function, and we strictly just added or subtracted. So that was a vertical shift. And I feel like vertical shifts do exactly what you think it should do. A plus means you added it, and so you're shifting which direction? Up or down, if you're doing a plus. Does everybody agree that a plus would move it up k units? Again, it's just being generic, but that case in ours is a 2, so it moved up 2 units. And then what's a minus going to do? Shift it down k units. All right, so then the horizontal is the opposite, remember? So if we have a plus on the inside, and notice how it is. This k is on the outside. You have your function, and then you're doing something to it on the outside, where here, the shift is happening on the inside of the function. What do I mean by that? Notice this is still squaring, and so technically it's still the parent function of x squared, but that shift, that plus or minus, is on the inside of the square. So that's how we know it's horizontal. And we got to just remember it's the opposite of what we think we want to do. So adding something's actually shifting it what direction?
To the right. Wait, left.
Right? It's the opposite of what you think. To the left, how many units? H units. So subtracting h is actually moving it to the right. H units.